Namaskar. Today we will discuss about regional metamorphism of Peltic rocks. We have already discussed in detail about the intermediate pressure temperature facies, which contain Zeolite facies, Greenschist facies, Amphibolite facies and Zeolite facies. In this topic we will discuss in detail, particularly for the Peltic rocks, how the Peltic rocks metamorphosed right from Zeolite facies up to Zeolite facies, with a special reference to AFM diagrams and important reactions. Regional metamorphism of Peltic rocks. Content: first, introduction. Second is Barovian Facies series. Third, characteristic minerals of Peltic rocks. Fourth, metamorphism of Peltic rocks. And fifth is conclusion. Introduction. On the basis of pressure and temperature, we can divide the metamorphic facies into three types, mainly facies of low pressure, facies of intermediate pressure and facies of high pressure. Mayasiro originally recognized three different facies series. First, a Zeolite, Prehenite, Pumpelite, blue schist eclogite type. Second, a typical Barovian type characterized by Greenschist, epidote Amphibolite, Zeolite type characterized by paragenesis of kyanite sillimanite type. And third, an Abukama type of Greenschist, Amphibolite, Zeolite characterized by paragenesis of Andalusite sillimanite type. Faye et al. In 1958 divided the metamorphic facies into two types on the basis of pressure, that is contact metamorphics, where pressure is less than 4 kilobar, and regional metamorphism, where pressure is more than 4 kilobar. Regional or Barovian metamorphisms covers large area of continental crust, typically associated with mountain ranges, particularly subduction zones or the roots of the previous eroded mountains. The regionally metamorphosed rocks occur during anorogenic events, the collision of two continental plates or iceland arcs, with continental plate produce the extreme compressional forces required for the metamorphic changes typical of regional metamorphism. The facies of intermediate pressure or Barovian type in order of increasing temperature and pressure of metamorphism, that is first Zeolite facies, second Greenschist facies, third Amphibolite facies and fourth is Zeolite facies. Barovian facies series. The Barovian facies series occurs in a number of Paleozoic mountain belts as well as in some of the Precambrian age. The classic region in the Scottish Highland. Other belts with Barovian rocks occur in Colorado, British Columbia, Alaska, Venezuela, Spain, South Europe, Asia, Japan. Precambrian belts of Barovian rocks occur in Black Hills of South Dakota, the Rocky Mountains, Labrador, Ontario, Canada and Singhbhum in India. The Paleozoic orogenic belts are clearly associated with convergent plate margins. Both Barovian and Buchan facies series developed at such margins. In convergent zones, regional heating due to the rise of plutons into the overlying plates, the plate above the subduction zone is the general cause of metamorphism, but migrating fluids may also transport heat. The zone of metamorphism in the Scottish Highland, originally described by Barrow in 1893, includes 6 distinct index minerals: chloride zone, biotite zone, almandine garnet zone, staurolite zone, kyanite zone, and sillimanite zone. The lowest grade in the zeolite facies, which form under the condition just above those of the diagenesis assemblages, is characterized by clay minerals. Assemblages may include kaolinite, illite, chlorite, quartz, analcite. At a strongly higher grade condition, assemblages of the zeolite facies are replaced by those of the prehanite pumpelite facies. As the PT condition increase, Greenschist facies assemblages with new minerals form. Typical assemblages in Peltic rocks include white mica, chlorite, chloritite, quartz, albite, magnetite, biotite, epidote, garnet, pyrophyllite, kyanite, almandine garnet zone of the Greenschist facies. The Greenschist Amphibolite facies boundary is a broad zone. The disappearance of albite marks the beginning of upper limit of the Greenschist facies. Thus, albite, like pyrophyllite, is absent from Amphibolite facies rocks. Staurolite rather than chloritite occur in the lower part of the Amphibolite facies, and the aluminosilicates, kyanite at low grades and the sillimanite at high grades characterize aluminous bulk composition. Typical assemblages include white mica, chlorite, biotite, quartz, plesioclase, garnet, magnetite, staurolite, ilmenite, kyanite, sillimanite, etc. The gammolite facies is distinguished by the general absence of white mica and the presence of orthopyroxene and plus minus cordite. Peltic assemblages include biotite, garnet, sillimanite, potash feldspar, andesine, quartz, plus minus cordite, orthopyroxene, sillimanite, zircon, etc. The quartzo-feldspathic rocks differ from the Peltic rocks. Quartz and feldspar are the dominant phases rather than the phyllosilicates, and the calcium-bearing phases are common. Additional minerals that may occur include stabilite, calcite, stiplomelanin, actinolite, and hornblende. Characteristics of Peltic rocks. Pelites, the Greek paleos means clay, is a descriptive names for a clastic rocks with a grain size of less than 1 by 16 millimeter. Originally sand or silt. Example include slate and mudstone. Second, pelite sediments are very fine grained, commonly size less than 2 millimeter. Mature clastic sediments derived from the weathering and an erosion of continental crust. Third, the mineralogy of Peltic sediment is dominated by fine alumina potash rich phyllosilicates such as clay, montmorillonite, kaolinite, etc. Fine white micas, that is silicite, paragonite or fensite, and chlorite, all of which may occur as a detrital or orthogenic grains. Fourth, other common constituents include feldspar, both albite and potash feldspar, iron oxides and hydroxides, zeolite, carbonates, sulfides, organic matter, etc. Fifth, the chemical characteristics that distinguish Peltic rock from other common rocks are high Al2O3 and K2O and low CaO. 6. Next, the high proportion of mica in metapelites result in the common development of foliated rocks such as slate, phyllite, schist and gneisses. Increasing pressure and temperature condition, cell change into slate and slate change into phyllite, phyllite change into schist and schist change into gneisses with low grade, intermediate grade and high grade of metamorphism. The index mineral which define a zone does not originally disappear when entering the next higher grade zone. For example, the first appearance of biotite is at the biotite isograde, where chlorite is seen to be reaching to produce biotite. Biotite does not disappear at the garnet isograde, and we can continue seen through the garnet, stolite, kyanite and sillimanite zones. Stolite, kyanite and sillimanite only occur in the stolite, kyanite and sillimanite zone respectively. The textures structures of the rocks change from slate, phyllite, schist, gneiss, slate and phyllite in the chlorite zone to different type of schist in the biotite, garnet, stolite and kyanite zones, and the normally gneisses in the sillimanite zones. The composition of the plagioclase change with increasing grade of metamorphism. It is nearly pure albite in the chlorite and biotite zone and becomes somewhat more calcic, oligoclase and andesine in higher grade zones. During Barovian type of metamorphism, where pressure, middle grade of metamorphism are higher than that of the aluminum silicate triple point, the resulting aluminum silicate minerals sequence is kaolinite, pyrophyllite, kyanite, sillimanite, which we can observe in AKF, AFM diagrams for feltic rocks. The presence of either kyanite or andalusite on metamorphosed cells and siltstone at the middle grade of metamorphism is one feature that distinguishes the regional Barovian type with contact bouquet type Facies series. The metamorphism of peltic rocks with the individual detailed studies of different facies formed during regional or Barovian type of metamorphism, that is from Zeolite, Greenschist, Amphibolite and Zeolite facies metamorphism. We understand the rock of similar bulk composition developed dramatically different mineral assemblages in response to different set of pressure, temperature, condition, or rock with different in bulk composition will develop different mineral assemblages in response to the same pressure, temperature condition. If we compare all the facies during regional or Barovian type metamorphism, the different zones were based on the first appearance of a particular minerals called an index minerals, which is characteristic of the zone. These boundaries were later called isoguards, equally grades and likely represent subfaces in a three-dimensional sense. Zones, textural type, mineral paragenesis in peltic rocks. Chlorite zone, slate and phyllite, quartz, chlorite, muscovite, albite. Biotite zone, phyllite and schist. Biotite begins to replace chlorite, quartz, muscovite, albite. Almandine zone, phyllite and schist, quartz, muscovite, biotite, almandine, albite. Stolite zone, schist, quartz, biotite, muscovite, almandine, stolite, oligoclase. Kyanite zone, schist, quartz, biotite, muscovite, oligoclase, almandine, kyanite, sillimanite, gneisses. Quartz, biotite, muscovite, oligoclase, almandine, sillimanite. For detailed understanding of the regional or progressive metamorphism of peltic rocks, we have to take the help of certain diagrams like ACF for Zeolite facies, AKF and AFM diagrams for Greenschist, Amphibolite and GEOLOGY facies. We have to concentrate on Peltic assemblages, and on the basis of the diagram we can find out the important assemblages and related reaction to explain the regional metamorphism of Peltic rocks. Now take up the first facies, that is your Zeolite facies. The characteristic minerals of Zeolite facies are lawsonite, lomentite, prehnite, pumpelite, quartz. No chemical reaction take place. Figure 1 is sedimentary environment, temperature is less than 200 degrees centigrade. And figure 2, characteristic of the Zeolite facies, important reaction, disappearance of clay minerals, and the reaction is analcime plus quartz give rise to albite plus water. Second important reaction is your hollandite give rise to lawsonite, lomentite plus quartz plus water. Third reaction, kaolinite plus quartz give rise to pyrophyllite plus quartz. Fourth reaction, lawsonite plus lomentite plus quartz give rise to pyrophyllite plus epidote plus water. Next reaction, montmorillonite give rise to pyrophyllite plus epidote plus chlorite plus water. The disappearance of lawsonite, lomentite, prehnite, pumpelite, montmorillonite, kaolinite marks the upper limit of Zeolite facies and also the lower limit of Greenschist facies. Greenschist facies. The Greenschist facies include the common product of low-grade, regional and dislocation metamorphism. The beginning of Greenschist facies is characterized by the following reaction. Kaolinite plus quartz give rise to pyrophyllite. This reaction was carried out by Thomson at 325 degrees centigrade 1 kilobar, 345 degrees centigrade 2 kilobar, 375 degrees centigrade 4 kilobar. The characteristic minerals Greenschist facies are characterized by the abundance of green color minerals, example chlorite, epidote, actinolite, chloritoid occur in Peltic schist that are richer in FeO and Al2O3 and poorer in K2O. Other diagnostic minerals are mica, muscovite and biotite, microcline, pyrophyllite, kyanite and garnet. Subfacies and zones of Greenschist facies. Mineralogical change in Peltic schist as the classic chlorite, biotite and almandine garnet are isogrades of Barov are used to divide the Greenschist facies into three subfacies oblique zones. Zones and subfaces, the chlorite zone, quartz, albite, muscovite subfaces, biotite zone, quartz, albite, epidote, biotite subfaces, almandine zone, quartz, albite, epidote, almandine subfaces. Now take up the chlorite zone, AFM and AKF diagram of chlorite zone. The Peltic assemblages are first pyrophyllite plus chloritoid plus epidote plus minus albite plus minus muscovite plus minus microcline plus minus quartz. The rock may be phyllite and schist depend upon the structure present. Second, pyrophyllite, chloritoid plus minus chlorite plus minus epidote plus minus albite plus minus muscovite plus minus microcline plus minus quartz may be again phyllite and schist. Third assemblage is your chloritoid, chlorite plus minus epidote plus minus albite plus minus muscovite plus minus microcline and plus minus quartz. This may be phyllite and schist depend upon the structure. Fourth assemblage is your pyrophyllite plus chlorite plus minus epidote plus minus albite plus minus muscovite, microcline and quartz may be phyllite and schist. Fifth is your chlorite, epidote, albite, muscovite, microcline, quartz may be phyllite or schist. Now come to the second higher zone, that is your biotite zone. The beginning of biotite zone is indicated by the appearance of biotite by the following reaction: 5 chlorite plus 3 muscovite give rise to 3 biotite plus Al rich chlorite plus 7 quartz plus water. Kyanite appears in place of pyrophyllite by the reaction pyrophyllite give rise to kyanite plus quartz plus water. This reaction was carried out by Carrick in 1968 at 430 degrees centigrade 3.9 kilobar and 400 degrees centigrade 1 kilobar. The Peltic assemblages are: first, the chlorite, chloritoid, plus minus epidote, plus minus muscovite, plus minus albite and plus minus quartz, that is also known as kyanite chlorite schist. Second assemblage is your kyanite, chloritoid, chlorite, plus minus epidote, plus minus muscovite, plus minus albite, plus minus quartz. In short, this is also known as kyanite chloritoid chlorite schist. Third assemblage is your chloritoid plus chlorite plus epidote plus minus muscovite plus minus albite plus minus quartz, is also known as chlorite chloritoid phyllite oblique schist. Assemblage fourth, chlorite plus minus epidote plus minus muscovite plus minus albite and plus minus quartz. In short, this is also known as chlorite schist. Fifth assemblage is your chlorite plus biotite plus epidote plus muscovite plus albite plus minus quartz, is also known as biotite chlorite schist. And sixth assemblage, biotite plus minus epidote plus minus microcline plus minus albite plus minus quartz. In short, it is also known as biotite schist. Seventh assemblage is your muscovite plus quartz plus chlorite plus biotite plus minus epidote and plus minus albite, is also known as muscovite biotite chlorite schist. Now come to next higher zone, that is your almandine zone. The first time appearance of almandine is indicated by the beginning of the almandine zone of Greenschist facies. The important reaction FeMg chloride plus quartz give rise to almandine plus Mg chloride plus water. Fe rich chloride plus muscovite plus quartz give rise to almandine plus biotite plus minus kyanite plus minus water. The Peltic assemblages are: first, the kyanite plus chloritoid plus minus epidote plus minus muscovite plus minus microcline plus minus albite plus minus quartz, is also known as kyanite chloritoid schist. Second assemblage is your kyanite, chloritoid, almandine plus minus epidote plus minus muscovite plus minus albite and plus minus quartz, also known as kyanite chloritoid almandine schist. And third assemblage is your chloritoid plus almandine plus minus epidote plus minus muscovite plus minus albite plus minus quartz, is also known as chloritoid almandine schist. Fourth assemblage is your kyanite, chlorite plus minus epidote plus minus muscovite plus minus albite and plus minus quartz, is also known as kyanite chlorite schist. And fifth assemblage is your chloritoid, almandine plus chlorite plus minus epidote plus minus muscovite plus minus albite and plus minus quartz, is also known as chloritoid almandine chlorite schist. Sixth assemblage is your almandine, biotite plus minus epidote plus minus muscovite plus minus albite and plus minus quartz, is also known as almandine biotite schist. Seventh assemblage is your chlorite plus biotite plus minus epidote plus minus muscovite and plus minus albite quartz, known as chloride biotite schist. Eighth is your biotite microcline plus minus muscovite plus minus epidote, quartz and albite, also known as biotite schist. Now switch to higher grade of metamorphism, that is your Amphibolite facies. The appearance of a stolite is indicator of upper limit of the Greenschist facies and the beginning of Amphibolite facies. The diagnostic mineral assemblages restricted to this facies are hornblende plagioclase anorthite 15% with plus minus epidote, or second the hornblende plagioclase anorthite 15 plus garnet. The characteristic minerals are stolite, gracilorite, garnet, almandine, diopside, cummingtonite, anthophyllite, sillimanite, orthoclase, etc. Disappearance of andalusite and corderite distinguish peltic assemblies of the amphibolite facies from those of the hornblende hornfels facies of lower pressure thermal metamorphism. Metamorphic zones and subfacies. The amphibolite facies are divided in 4 different zones, that is your stolite zone, stolite almandine subfacies, kyanite zone, kyanite almandine subfacies, sillimanite muscovite zone, sillimanite muscovite almandine subfacies, and sillimanite orthoclase zone, that is also known as sillimanite orthoclase almandine subfacies. Conclusion: the course content on regional metamorphism of peltic rocks begin with the introduction, followed by the description of introduction, characteristics of peltic rocks, metamorphism of peltic rocks, with a detailed comparison of geolite to gaolite facies with the help of ACF, AKF and AFM diagram. Important reaction during prograde metamorphism of peltic rocks, and also observe the important changes in peltic rocks. Thus, on the basis of the detailed study of different subfacies and also with the support of experimental data, we can conclude that during prograde metamorphism of peltic rocks, different rocks are formed like slate, phyllite, schist, gneiss and peltic gaolites. In this modules, we have covered the peltic metamorphism of geolite facies as well as greenschist facies. Thank you very much.